Hello, everyone. Welcome to today's session. We are looking at hash functions, part 2. So let me see what states we are joining from today. Ahmed Aga is from Yobe State. I can see Mohammed G. Boy, Bat Sheyi, Mohammed G. Boy, yeah, Stanis Salisu from Gombe, Aminu Ibrahim. Yes, welcome to Hash Function Part 2. Awal Ahmed from Kano, Aminu Ibrahim, I can see you. Ahmed Muhammad from Duse, Jigawa State, Muhammad Jiboya, Abdullahi Ledan, Musa Ibrahim, Aminat Zubeiru, Sanib International Co. He's Tani Muhammad, sorry, from Kano State. Usman Ibrahim, Ahmed Muhammad from Adamawa State, Gidan Magun Mushinship, Tani International. Hello, Mukhtar Muhammad from Borno, Ibrahim Abdulaziz from Katsina State. I'm from Gombe, Samira Abdullahi Muhammad Adam from Jalingo, Taraba State. Basi Asuko, Mutala Nesia from Katsina. Halima Dala from Gombe State. Shibweze Nwakama from Delta State. Bashir Abubakar. Okay, Hamza Tuko. Yes. Salam. This is Awa Abdullahim. Abdul Hadi or something from Borno State. Okay, Aminu Ibrahim from Yobe. Hamza Tuko, I've seen you. Nasru Dalatu from Zamfara State. So, okay. So, yeah, I can see Binta Muhammad. He said Ramadan Kareem from Maiduguri. Yes, Ramadan Kareem to all our Muslims here. As you observe the Ramadan. Nuhu Iyayi. I'm from Lagos. I see Azoka Abraham Nduka. Okay, so we'll have to jump right into what we have for today. Let me share my entire screen. Stop share now. Yeah, my screen. Yeah, that. And yeah. So the last class, we started looking at hash functions. And this is a basic computer science course. I mean, if you ever do computer science in the university, you most definitely will have done hash function, most definitely, right? Because in Bitcoin in particular, hash function is like a primitive. They're part of the primitive. We have the hash function, we have the Merkle trees. They are all primitives. When we say primitives, we mean the building blocks. So if you're going to be a blockchain developer, you need to know and understand what hash function is, even if you don't know all the technical stuff about it. But you need to have a general overview of what hash function means. When they say hash function, you understand, okay, this is it. Then if you're building something, at the point of building, you can then go look up specific instances of what you're building and how it's implemented. You just read that part and implement your own part. But it's a primitive. Like in computer science, when we say data primitives, for every language have a primitive. I'll give you an instance. Integer. Integer is a primitive, no matter what programming language you're using. Integer, int, okay, it's a primitive, it's a building block for so many other things. And it has operations associated with it. So when you have an int, if a data is an int, for example, then you can do addition, you can do subtraction. Those are properties of that primitive. So you cannot then use it to form other maybe derived operations, depending on what you're building. So hash function in Bitcoin development is part of the building block. We started looking at it from the last class. So today we're just going to continue where we stopped. So there are three important properties of hash function. Number one, pre-image resistance is one way. Number two is second pre-image resistance, and this means it's deterministic. And number three, collision resistance. So let's look at number one. When we say pre-image resistance, that is one way. What does that mean? Look at the diagram by my right rather. So we have an egg. You break the egg. And when you break egg, two things happen. You spill it, right? So you have two components. You have the yolk and you have the white. So if you break an egg and the yolk and the white, you turn them very well, mix them up using your mixer or anything, or if you can even beat it with your fork, right? I mean, it's common to use fork to beat egg. So the moment you do that and probably boil it, you scrambled it. And once you scramble an egg, you cannot go back to getting that egg back. Once you mix both the yolk and the white, right? And if you apply heat to it, you can't go back to having that egg. It's a one-way thing. So when we say pre-image resistant, it means that given a hash value, it is computationally infeasible to determine the input data that produce the hash value. So looking at, if we'll show you, we'll give you, say, hey, this is the hash. It's a fixed length of bytes. It's a fixed length of bytes. So once you look at it, you cannot know what input generated that. You can't know. That's it. It's a one-way thing. So it's okay, you can see it. That's why you can share your, for example, your address, your Bitcoin address, for example. You can't guess what the, you cannot guess what the input was. Maybe what private key was used to generate that. You cannot guess it by looking at the, sorry about that. I'll turn my phone off now, put it in silent. So it's a one-way thing. So going back to our analogy, going back to the analogy we're having here, we say that when you scramble an egg, you cannot unscramble it back. Chemist guys might differ a bit, but yeah, you can unboil an egg, but once you scramble it, you can't go back. And let me explain that. So when you break an egg, for example, you take only the white and you boil it very hard. It denatures the protein because it's protein. It denatures the albumin, they're all protein. So when it's denatured, right, it's possible to treat it with maybe urea overnight, some urea and compound overnight. After treating it, you put it in a vortex, shake it very well, spin it up, and it interacts with the wall of the vortex, whatever tube you put Okay, hello. I think there was a reset or something. I lost my mic went to, got muted. I think that's solved now. So get back to, yes. So yeah, so you can unboil an egg, just only the white. You do that with the white only, treat it with some urea, you get back your white. But once you scramble an egg, you cannot go back to having that egg. So you won't know what it is. So when we say something is pre-image resistant, you can't look, if we give you the hash, it's okay to give people the hash. You look at the hash, but you can never from the hash guess what it is that gave rise to that one. So what does it do? It prevents an attacker from discovering the original input data by analyzing the hash value. That's what we say is pre-image resistance. So that's one of the functions. Now think about it. If it's not pre-image resistant, then it doesn't solve any problem for us, because once you hash it, somebody can decode what it is, and from there, you can attack, you can change value and do whatever you have to do, the attacker wants to do. So look at the second property. It says second pre-image resistant. So the first one is just pre-image resistant. Looking at the hash value, you cannot determine what the input was. Now, in this case, we say second pre-image resistant. Now look at the diagram there. So in this case, the message digest of the hash function is consistent and giving the same input value. So what is saying that each time I have an input value that is the same, it will always give me the same output. So if you hash, for example, in the image we have where we have, let me wait for it to come. Consistency is key. That's the word. It says consistency is key. So if you hash consistency is key, it gives you that, the hash value. If you do that 1,000 times, you're going to have the same value 1,000 times. So it's deterministic. I could say that I can beat my chest and say, each time I hash this particular value, I must have to get this other one. So hash functions are deterministic. The same input produces the same output hash every time. All right. So let me see. I have to, let me clear this. It's so untidy. Okay, so what was that word we saw there again? Let me look at the slide. 1 minute. Yeah. So it says, it says consistency is key. All right. Consistency is key. Let's try that out. So I'm in my terminal. Again, I'm using Mac OS. So it has the SHA-256 installed in it. I think you can also do that on your machine. I'm not sure if it comes native with the operating system. I'm not sure. I know I've done so many things about cryptography. I can't remember if I had to install it or not, but whichever way you can. So there's this program called OpenSSL. Okay, before that, let me write. I have a text file here called sha_input.txt. Let me see the content. Cat sha_input.txt. Okay, I already have that. So inside this file, I have this word, consistency is key. You can see that. What I just did, I pulled up the input or whatever is in that file, try to send it to the terminal, and it said consistency is key. Okay, so let's hash that and see what we have. OpenSSL SHA-256. That's what we are going to use, and the file here is _. You can call your file anything. So I hashed that, see what we got. It started from 514 here. We started from 514B and end with 66E. So let's try to hash it again. We say it's second pre-image resistance, which means it's deterministic. If given a particular input value, I can beat my chest and say, I'm going to have what I had before. So let's try that again. Open SSS, SHA-256, I pass the file to it. It's a simple way you can pass file to it. And again, we started with 514B and end with 66E. So if you can, you could write a simple program that will do it and put it in a loop, all right? So just in that loop, you can run it 1,000 times. You'll see that you get the same value that 1,000 times. That's what that property is trying to say. Okay. Back to my slide. So let's look. Someone is calling me from Telegram group. I assume it's a student. I hope you guys can hear me. Let me see. Let me check the chat. Your screen is not shared. Oh, I'm sorry. Someone said my screen is not shared. Okay. Sorry about that, man. Let me share my screen and repeat that. Okay, I guess you can see my screen now. Thank you very much for calling my attention to that. Thank you so much. All right. So I'll just go back to my terminal. Let me clear this up. Clear. All right. So if you look over here, I have my file. This is VS Code. So on the Explorer part, you see this file called *_input.txt. Look at what we are trying to achieve. Let me go back to the main slide, 1 minute. So in this slide, we're looking at the second property. We said the first one, pre-image resistance. Okay. Then the second one is second pre-image resistance. And we're saying that what this means is that the message digest of a hash function is consistent, given the same input value. So as long as you have the same input going on, the digest, whatever, you know what the digest is by now, the value of the hash, when you hash it, that fixed length you bring out for you is consistent. So you can beat your chest and say that in this, our example, we say consistency is key. So if I hash consistency is key, using SHA-256, for example, I will get the same digest. I will get the same hash value. Do it 1,000 times, we get the same thing 1,000 times. So here in VS Code, so I have this file called SHA_input.txt. I just created it. And let's see the contents. I can see the content with cat. I know it's small, so it won't see the whole screen. So cat *_input.txt. You see, it says consistency is key. So that's it. Now let's hash this. Okay, I have my program, my SHA-256 program here. I'm using Open SSL SHA-256. That's what I'm using. You could want to do SHA-512, whatever one, but we are using SHA-256 to do this. And we'll pass the file to it. So normally you have to pass your file to the hashing program. Whatever hash you want to, you must give it what you want it to hash. You could pass the string literally or the file, depending on the implementation of that program. So in this case, you can pass the file. And the file is SHA_input.txt. We know what it contains there, just consistency is key. Now, enter. You see what we have. We have the digest is 514B, started with 514B and ended with 666E. right? So let's do it the second time. I run the same command again. If you run a command before, I've just press the arrow key if you bring back the last command. So I don't need to retype it again. I just hit enter. And let's look at the digest again. Start with 514B and end with 666E. Same thing with the other one. Okay. You run it a third time. This property says that if we do the same input, we must have the same digest. Again, that's it. So I say, even if you write a program and loop through this command and say, hey, run it 1,000 times. If we give you, as long as it's the same input, you didn't change the input, you get the same value. So this is one of the properties of a SHA, 256. All right. So go back to the slide. So the next thing there is, let me move this out of the way. Okay. So hash function is collision resistance. So what does this mean? It means that it ensures that it is computationally infeasible to find two input messages that produce the same hash value. So you can't find two input messages. Those inputs, they will be different. Remember, if it's the same message, it will give you the same. But when we say collision resistance, remember when we talked about constructing a hash table in the last class. So when how it does it, it hashes that based on whatever it gets, you know where to go put it, a bucket. It's not serial. You could hash something, go put it at the bottom because that's where it's supposed to go to. It hash another one, put it in the top, So it does that. Now, you cannot hash two different messages and get the same hash value. Getting the same hash value means you have to, let's say you hash the first one. In this case, I am unique is an example. And the second one is I am unique too. You can see that I am unique too. Now, if you hash these two different things, they will not give you the same hash value. Because if they give you the same hash value, it means there's collision. You know what that means? An attacker can change the value because you have some things installed here. I'll do another stuff. Maybe you've written a data to a particular bucket, right? Then I don't even know what your input, but I use my own another input, replace that data because it will hash to that same bucket. So it's a good hash function will not allow collision. That's what we try to say, right? So if you have I am unique, let's go back to our script and see. Though you could know that this will work, but let me clear the screen. Yeah. Okay. Clear. All right. So I am unique. So we'll make two files. In the first file, let's overwrite it. So I'll overwrite what we have here before with I am unique. Okay. So I'm redirecting this output echo. Echo command is just a way to direct your, to send something, whatever string to wherever. It could be your terminal, it could be a file. In this case, I want to take it to a file. So, and the file is input.txt. I'm overwriting it. That's why I'm using one greater than sign. If I wanted to append, I'll use double. This greater than sign here, I'll do it 2 times, but I want to overwrite. So let's see that it overwrote it. So I cut that file again. You see what we have there is I am unique, right? So let's make a second file. Let's call it, let me make a second file. Touch input 2. Let's call it 2.txt. Okay, so you can see here we made a new file, but it's empty. You just use the touch to create an empty file. If we cut this file, we won't see anything in it. Let's see. input2.txt. See, is blank. It didn't show anything. So in this case, let's put I am unique 2 to it. So echo I am unique 2, right? And where are we sending it? To send it to char input 2.txt. Here we go. All right, let's confirm that. So I cut, clear this for now, clear the screen. So I cut char input 2.txt. So what we have there is I am unique 2. So let's get back to what this is trying to say, collision. Collision is saying that it ensures that it is computationally infeasible to find 2 input messages that produce the same hash value. So in this case now, in the first one, we are looking at the hash. In the other ones, the pre-image, and we're looking at, you see the hash and you cannot find what the input is. In this collision part, okay, so if I give you 2 different messages, you cannot use them to produce the same hash. They have to be different. That's all it's trying to say. So let's run that and see what happens with it. And here I'm back. So collision, what we're going to, okay, let's open SSL *256. And we do the first file, normal. So the first file is *_input.txt. Oh, sorry, I made a mistake in the command. I typed sh256. I didn't put the A, *. So let me clear the screen and run that again. So I could just call up the command. I have to retype it. I go and edit it, put *. Okay, *256. And we pass the first text to it, text file. It gives us a digest, right? So let's do the second one. In the second, we only added 2 to the second one. Let's see what happens with it. So in this case, instead of *input.txt, we are doing *input2.txt. That's the second file. And when I run that, now let's compare. The first one is start with 199A and end with 688BF. Second one start with FA8. So you can see they are not the same. And the thing is, even though they look similar, because I am unique, one is I am unique, the other one is I am unique 2. We only added 2, but the fingerprint, the digest, is nothing close to them being the same thing. Some totally different, just by adding a single dot, right? You get something totally different. You can't even guess they are related in any way. So a good hash function will be able to avoid collision. Whenever you have collision in anyone, then it's not a good one. Along the course, we'll see what happened. When we're looking at the history, we'll see cases where there are some hash function, early hash function that later had an issue and they had to be discontinued. So that's what hash does. These are primitive. As a blockchain developer, you should know about hashes very well. And because that's the basis of when we say you cannot tamper with it, a data, you cannot attack it. These are the basic stuff we are looking at. It's a primitive. Okay. So let's look at the hash function that we find in Bitcoin. So there are many hash functions, there are many implementations, but for Bitcoin, which is what we are studying, what are the hash functions there? So we have the Merkle-Damgard hash function. This is the first major implementation of hash function that really works. Merkle-Damgard, those are the name of the people involved, okay? And the hash function. So let me use the diagram to explain it before I read it out. Now let's look at the first blocks, the upper part here. So we have, okay, let me say this. Now, what it does, you give it an arbitrary number of data, message, arbitrary. What it does is break them down into blocks. That's what it does. because you need to know if it doesn't know the length, how is it going to calculate it? So what it does, here we have a long message, okay? Now it breaks them into blocks. And what it tried to do here, it used predefined, like you have, in computer is binary, and the base 2, it's easier to do computation using base 2, right? In fact, I should say the hash function uses predetermined basis to do. If you use any arbitrary stuff, it might fail one of those tests we are looking at. So in this case, it might say, okay, I'll divide everything into 256 bits or 512 bit. So you see block message 1, let's assume it's using 256 bit, okay? So as the message comes, it will, here is the message, block 1, block 2, block 3. Now, there's a problem here. So if I have a message that say, let me use something simple, the week, days of the week. We have 7 days in a week, yeah? So if I give you 20, let me say 29 days, yeah? No, let's say 20, if I give you 22 days, and we want to break them into 7. So 22 divided by 7 will give you 3. We go into 21, remember 1. So you see that the first one will be 7, the second one will be 7, the third one will be 7, but the last one will not be 7. It will only be 1, remaining 1 digit. And that 1 digit, like we say, it doesn't meet your base. In this case, we are using a 7 as a base when we're looking at week. We're divided by 7. So we're using 7 as a base. So you have a block of message. So problem with this now, if you divide them up, it's possible to have extra data that is not up to what you need, because we want them to be in 7. So what does it do? Here is what look at the solution in the middle. You have block 1, block 2, block n, that's the last block. Then whatever is left, it will pad it up. It will add some padding to it. You know what it's trying to do? To make it up to, let's say, 7. So in this case, we have only 1. We'll just add 5 to it. Sorry, we'll add 6 to it to make it 7. But it knows, it is binary, it knows where it added it, and it knows how to take care of that. So the first thing it does is it breaks the messages into blocks. And the last block, it will check if it's less than whatever it's using, maybe 128, 256, 512. If it's less than it, it make it up to whatever. So there's a padding that happens here first. So after this padding happens, you know what it got now. So you have some initial vector, it adds to it. So it passes it through a function. Don't worry about the function. This is a design. Remember, this was designed by Mecker and Damgard. They have a paper for it. If you're more interested, you could go pull up the paper they used to publish this and look at it. So here, it just passes it through a function, f. So what does it do? It brings message block 1. It adds some initial value to it, okay? And hash this. Whatever the output is, when it hash this other, it gets this other message here, it adds whatever I had before to it and hash it again. So it's a continuous string. You keep, get the input of the previous block, add it to the new block, hash them together. So it continues like that. And at the end of everything, you have a finalization. It does another stuff here before it gives you the final hash. So why did they do all these things? They are trying to make sure that it have those properties: pre-image resistance, second pre-image resistance, and collision resistance. There's a whole mathematics on how that happens. We are not discussing that beyond the class, right? So, but just know that this forms the basis for building most of the hash. If you're a core computer science student and someday you want to implement hash from scratch, you could turn back to this solution to try to implement yours. So that's what happened. So let me read through that. So it breaks up the input message into fixed length blocks and process each block sequentially through a compression function. That's the F. This is the compression function, F. So the output of each compression function is then combined with the next block of data. And the process is repeated until all blocks have been processed. Now, the final output is a fixed length digest or a hash value that is unique to the message. After finalization, I give you the hash. And this hash will be unique to this particular message. So this is widely used for building hash functions that process input messages of arbitrary length and produce fixed length output. So this was the beginning of the whole stuff. Some of the hash implementation we'll look at in subsequent slides are based on this Merkle-Darmstadt hash function. I have a reference to this image. I pulled that off from Wikipedia. I have the reference there, so you could look it up. Okay, so in Bitcoin, what are some of the hash we use? The major hashes we use in Bitcoin is the SHA-256 and the RIP-MED 160. SHA-256 and RIP-MED 160, those are the two. And let's look at this table. This table is in the portal, it's in Fitwork portal. So, but we're just going to go through it right now. So we have SHA-256. The output length is 32 bytes, right? So what does it do? It generates unique 256 bits from input string. So give it any input string, it will give you 256 bits of data, unique. Okay. What are the common application in BSV? We use it for proof of work algorithm and for address creation. So those are the two places. SHA-256 for proof of work. We'll see that when you're trying to look at the headers and everything. And also for address creation, when you're creating an address, you want to create a new address, a Bitcoin address. You use this SHA-256. So another implementation is the RIP-MED 160. This uses a fewer byte. It's 20 bytes, right? It generates unique 160-bit value. You can see 256 generate 256. This RIP-MED. So when you see these numbers attached to them, it tells you the number of bits the function generates. And it's also used in address creation, right? It's a decision you want to make when you're creating address. Which of them do you use? Okay. So we also have, you can also use SHA-256 for blocks and for transaction. So these are the two stuff we have here. If you look through, everything revolve around SHA-256 and RIP-MED 160. So that those are the common hash functions we use in the Bitcoin blockchain. Okay, so there's one implementation Bitcoin did from Satoshi Nakamoto. He introduced what we call the base 58. Now, what is base 58 and why do we use it in Bitcoin? Now, base 58 is a binary to text encoding of data to plain text. So let me explain what that's saying. So you give it a plain text, right? No, you give it a binary, zeros and one. It will convert it to a plain text to you. Binary could be anything, binary, you could have hexadecimal or even decimal. I think in the example I use here, I use decimal. So look at the image we have here. Let me wait for it to start all over. So in this case, you have a data. It converts this data to zeros and one binary. Look at that. From this binary, it converts it to something you can read. See, 2KNTJC. It's easy to understand 2NK blah 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 than to understand this 0111. We know what it is. You can convert. This is in base 2. You can use each octet, convert each octet to decimal to know what it is, right? So now normally we have base 64. The common thing is base 64. But see what happened. They dropped some of the common text we know. Yes. Let me pull up something here. Let me pull a text file. Okay, look at this. So before I do that, let's look at the reason that Satoshi gave for that. I'll read through this. This is from the Bitcoin white paper. So say, why base 58 instead of the standard base 64 encoding? So in normal encoding, you use base 64. So why did he use base 68? Well, you don't want 0 capital O, capital I, and L characters that look like the same in some fonts. So when you have address, remember, Bitcoin address used to be very long, right? Now, you just have some numbers. So it's easy to confuse 0 and capital O, for example. Now look at this. Let's go, let me call up this now here. So see 0. I type I'm not sure if it's too tiny. Let me zoom on this. I hope I can zoom in on this. Yeah, I can zoom in on it. Okay, great. All right, so here we have 0, like number 0. This is number 0. Then here's capital 0. Okay. Now look at I. Now look at 1. Now let's look at this. Now you see the first one is number 0. How do I know? There's a cross. They cross it like that. Okay. But assuming this first one is not here, let's remove it. Anybody that sees this capital O might think it is 0. Right? So you see, you can make mistakes. And you know, if you're trying to send something to an address and you send it to a wrong address, it's gone. Remember, it's not reversible. So you might send to a wrong address. And once that happens, that thing is gone. So it's easy to confuse number 0 with capital O. And also, look at I zoom in on this. If assuming sometimes if it's not zoomed in, you might think that this I is 1. You might confuse I and 1. And look at L. Let me put L. Small letter L. Now there's a problem. You might see small letter L and you might think, oh, it's 1, right? Because you might not be able to zoom in to see exactly. So there might be confusion here. So what he did is, okay, let's drop all this confusion. So in this case, rather than have capital, rather than have this 0, capital O, rather, let's use only small letter O. Let me put it side by side. Let me put small letter O. Now, it's very clear if you look at this. This is O. I cannot mistake it. I know this is small letter O, right? But this capital letter O looks like 0. So what it means, let's not use capital letter O. So it doesn't confuse, don't confuse it. So we can use 0. Anytime I see something, I know it's 0. Then if I see this small one, I know it's O. Then also L, since L, look at this L, it can confuse us. You might think it's 1. So rather than use it, let's not use small letter L at all. Let's use capital letter L. Now you cannot confuse this with 1. You see that? It's distinct. And again, I, you can confuse I with 1. So what did they say? Let's ditch I, use small letter I. Now you cannot confuse this. So what happened is, rather than having base 64, certain numbers were dropped. That's why we have 58. 64 minus 58, that's about 6. So about 6 alphabets were dropped. That's what it means. So because you drop them, you no longer have 64 ASCII characters to represent data. You only have 58. So you have to make a new encoding. Encoding just means a word. For example, base 2 is an encoding. You can have 10. I can give you the number 3, for example. I say convert it to base 2. 3 should be 1, 0, no, 1, 1, I think, yeah. So if you're starting from the least significant bit, you have 1, 1, then 0, 0, you know, not from the from the least significant bit. So you have 1 and another 1, because the second one is 2, the last one is 1, 2 and 1 is 3. So that's an encoding system. So you can have your own encoding system. You can say, hey, my own might be base 57. Though it wouldn't make sense. Why 57? But whatever it is, it could be base 56. 56 could make sense, right? So that's why we have base 68 encoding. Now, and look at some of the reasons he gave. Let me go back to the document here. He says, it could be used to create visually identical looking account numbers right? Now, a string with non-alphanumeric character is not easily accepted as an account number. So, of course, you don't have the plus and the minus, although it's only alphanumeric. Now, email usually won't line break if there's no punctuation. So, all it's trying to say, you want to convert into email, somebody's email, and you don't want to make mistake or address, Bitcoin addresses, and you don't want to make mistake. So that's why they have a new encoding called base 58. It's not cryptography this time. This is not cryptographic because it's just an encoding. You're just, and you know the baseline. So here's a table. Okay, so let's look at this table. Now, normally, here I have value is just the value here. I will have the base 58. Now, 0 in the base 58, 0 is represented by 1. So 1 is represented by 2 in base 58. Why 2 in base 58 is 3, and 3 in base 58 is 4, just like that. And when you get to 8, which means 9, then hexadecimal, but not just hexadecimal, we're using, it's hexadecimal, another encoding. I use 16, but this guy base 50, so we have 58 numbers. You can see the last number here is 57. If you add 0 to it, it's 58. That's why it's called base 58, because we have 58 up to here. 57 plus 0 plus 1 is 58. So you could see when we got to 9, 9 equals to A, capital A, 10 equals to capital B. So you keep going, B, C, D, E, F, G, H. Now see what happened. There's no I, there's no capital I. So it went sequentially up to, let me read it, A, B, C, D, E, F, G, H. There's no I, it jumped to J. So because remember we dished I, so no I, so that we don't, capital I, not small letter I, capital I, so we don't confuse it with 1. So we now have J, K, L, M, N. Now see, there's no capital O. We dished it, removed it. After M, we don't have capital O. We have P, Q, R, S, T, U, V, W, X, Y, Z. And it continues. We'll have to represent small letters too. We have A, B, C, D, E, F, G, H, I. You see, we have capital, we have small letter I, but we dish capital letter I because small letter I doesn't conflict with anyone. I, J, K. Now there's no L. Small letter L, we don't have it. Meanwhile, we have capital letter L. And why? Why do we have capital letter L? You cannot confuse capital letter L with 1. So it wasn't dished. But you can confuse small letter L with 1, so it was dished. So we have M, and we have small letter O. Remember, we dished capital letter O on the other side because it looks like 0, all right? So whenever you see O, okay, it's O. There's no mistaking it. P, Q, R, S, T, U, V, W, X, Y, Z. So on the whole, we have 57 plus this 0 plus 1 here, that's 58. On the whole, we have 58, and that's why I call base 58. Let's do a simple exercise on this to drive it home. I use decimal for this particular one. I already written it out to be faster, to make it faster for us. So we want to convert base 10 to base 58. Now this is a number 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't mean it in the sense of one. It's a, let me see, 1, 2, it's up to 9. So 1, 2, 3, 1, 2, 3. So we have 123,457,700. So it's a, I just want to say decimal number, but I just use 1, 2, 3 to, it's a decimal number. So how do you convert this to base 58? This is how it's done. So you start with the first number. Because it's 58, you divide it by 58 and you get the remainder. What's the remainder? When we did programming, when we did JavaScript and Go, we knew about this modulus here. Remember modulus. This thing means modulus. It means what is the remainder when is divided by this number. That's what it means. Yeah, we could use JavaScript. Let me pull up this guy. Okay. Yeah. Let's pull up the inspector, the console. So here is the console, the inspector here. I go to the console, right? I need the console. So want to use JavaScript. We can clear this. So yes, the number is 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, that's what we have. Now, what is the remainder? Remainder is modulus, right? Okay, let's get, when you divide it first, what do we get? Let's start with that. If you divide this by 58, just division. Now, we're not talking about, this is normal division. What is the mantissa side of it? What is the whole number part of it? We are not interested in the fraction part of it. So if I run this, we have 2128565. Let's check out our slide. 212. Okay, I can copy this, right? Yeah, anyway, 2128565. Let's see. You see that 2, but what is the remainder when you divide by 58? Let's go back and see that. So in the second instance, I want to find the modulus now. So for the modulus, when we say 1, there is it. So what is the remainder when you divide this by 58? Remainder is what? 19. Let's go there and see. So when you divide this by 58, you remainder is 19. That's what you write down. Remember, it's the same thing if you're converting base 10 to base 2, you divide by 2, right? When you divide by 2, you write what the remainder is. It's just the same thing. But when you say base 58, you divide by 58. If you're doing base 16, you divide by 16. That's it. That's just it, right? So you can continue like that. So when you divide 2128565 by 58, the remainder will be 23. Let's just confirm that more, and we assume every other one is correct. So now we want to divide 2128565. We want to find the modulus. What is the remainder when you divide that number by 58? The remainder is 23. Let's go see. And yes, we have 23. So we assume it's all correct, right? So, and this is what you get. If you divide this by 58, the remainder is 43. You keep going until it's less than 58. We now have 10. When you divide this by 58, remainder will still be 10 because it can't even go one part of it. And that it stops there, nothing to do again, because it's now, you have 0 here, because when you divide this, what you get is 0, remainder 10. So since it's 0, you don't continue dividing. And just like in this, you now start from the list from here and go up, right? So that's what we did here. We have 10, 52, that's this 10, 52, 43, 23, 19. Look at it, 10. I'm not sure why. I'll have to share my screen again. I'm not sure why I got disconnected again, but I hope you can see my screen again. Okay. Let me check. Can you guys see my screen? Let me look for the response here. Okay, I'm back. Good, good, good. All right. So where we are here. Okay. So we'll find that 10 means capital B. Now, what is 52? Let's see what 52 is in base 58. We go back here, we go to 52. Now 52 is small letter u. That's what it is, small letter u. And what do we have here? Yes, we have small letter u. And what is 43? Go look for 43. 43 is small letter k. And we have small letter k. And what is 23 here? We'll go back and see. What is 23? 20 is Q, uppercase Q. That's, yeah. And I think that's all we have. We have uppercase Q. And what is 19? We go back, look for 19. 19 is capital L. And yes, that's what we have, capital L. So that's a simple thing, you know. So you could do from binary. You know, it's just the same thing. Binary, you can use, can also take it to base 10 first. Yeah, in binary, you divide by 2. To convert back to base 10, you multiply. It's just like if I want to go back to base 10 on this, I can put this like this. This raised to power 0, this raised to power 1, this raised to power 2, this raised to power 3, this raised to power 4. So I can say 19 times 58 raised to power 0. 58 raised to power 0 is 1, you know, times that, plus. So you can go walk back in time and it will still give you 1, 2, 3, 4, 5, 6. So if you want to go back, you now multiply by 58 and maintaining the power. This will be 0, power 0, this is power 1, power 2, power 3, power 4. So you can go back in time. You could just practice it on your own and see. So encoding, so you can do your own encoding. Way back, you know, when communication wasn't so much like that, they used to write letters. You have to know the key to the letter. So you have to know the key. So I can say in my own encoding, you could say that C is A. You know, you can shift 3 spaces. You have A, B, C, D. I can start with D. So my A will be D, my B will be E, like that, like that. So you just write following that, you know, your encoding system. When you give it to a messenger will open, won't understand what is there. It doesn't know the key. It doesn't know, right? But the person you are sending knows the key. He knows how you people agree to. When he gets that, the person will shift by 3, then start reading it, and it will make sense to him. So that's just encoding. And so that's what it did here. It tried to remove ambiguity, remove all those ambiguous numbers. And if you look at, you will not see those ambiguous numbers in your address. I can imagine you're trying to send something to someone and you make a mistake. You thought it's a 1. You thought you see an L and thought it's 1 and you put 1. Maybe you might be lucky. It won't go at all, because if you put a wrong, you usually check. Read these days, if you put a wrong address, it checks, oh, this address is wrong, and it throws it back to you. You might be lucky. Oh, it tells it's wrong. You say, you know. But what if you put one and it's another person's address and you send something? Remember, it's irreversible. You are gone, really. So it's a good invention, I think. Now let's look at the second part of it, base 58 check. So what does the check do? Now we talk about base 58, but what does check do? Now, base 58 check is a modification of original base 58 encoding scheme. What does it do? It adds a checksum to the encoded data to detect errors and ensure data integrity. So what it does is you have an address. It does an address, for example. Okay, you have your address. Before it stores it on your machine, if you're using your device and somebody sends you a public his address with a public key, before you store, you won't know. You just store it on your wallet. Your wallet will run a program. What it does, it hashes that, of course, right? It gets a value. Then it takes the most significant bit, four bits of it, takes 4 bits of it, add it up to the end of it, pad it up, then do the final hashing that it stores it. So what happens is, if you want to, let's say somebody sends you his public key to send him some stuff, right? And assuming your machine has been compromised, you say, I have it, or is this address? Before you want to send it, at that point, maybe the malware in your machine will convert it to another address, which means you type the person address, but before you send it, the malware will convert to another address. Well, it can do that, but what the wallet will do, before doing that, you do a checksum. Because when it got that initially, it did those conversions and padding and stored it on your machine. So if you do that again, if the checksum doesn't correspond what's on your machine, on your hardware, it will fail. So that's one way of preventing attack also, preventing you losing your data. So it does a checksum. It does automatically without, you don't tell it to do, it does it automatically. So checksum, it happens in network when you're transmitting data, bytes, also bits, okay? When bit goes, or it has a checksum bit, it goes. It's, hey, I've sent this to you, but hey, I added 010 at the end. So when it gets there, it will check, does it have 010? If it doesn't have 010, there's a problem. This data is corrupt. So you have the payload, which is the real data, okay? But other things added to it. It checks some bit. The bit could be odd, it could be even, it could be even bit. So, okay, it's even. When we're supposed to be even, it gets an odd bit. You say, hey, there's a parity error here or something. And so checksum. So the checksum is calculated, okay, here, by taking a hash of the data to be encoded, yeah? Typically using the SHA-256 algorithm, and then taking the first 4 bytes of the resulting hash. These 4 bytes are appended to the end of the data to be encoded. And the resulting data is encoded using base 58 encoding. Okay, that's it. So it does all those things, append that before using base 58 to encode it. When it does it, it gives you a unique fingerprint that is just different from the actual address that was sent to you. So when you want to perform, it will do the same event with it and find out if they don't match, there's a problem. So checksum, if you just see base 58 check or just the checksum, just know it's a way of checking to make sure that data integrity is to ensure there's no error and there's data integrity. That's what it does. Okay, so SHA-256, a little bit of history. I'll just run through this because it's in the portal already. So SHA, SHA stands for Secure Hash Algorithm. Okay, I omitted a whole section, the section on MD5 and MD4. Why I omitted them? They are obsolete, never used anymore, but they are the precursor to SHA. We started with MD5, MD4, then MD5, but finally they found out that it could have collision, all right, and they were disbanded. In fact, it's still there. But I remember about 5 years ago, I was trying to use MD5 or something, and my computer was complaining. The operating system was telling me, so I didn't understand what that means. All right, just allow me use this thing. But yeah, now I know why. So the SHA-1, under this SHA, we have the SHA-1 set of hash functions. It was developed by NSA and published in 1993. So, and I want to say something. It is based on that Merkle NITDA we discussed before, where data are broken into chunks, right? And there's a padding that goes in before passing through compression function. and and LADA, and get to the end. So we have the SHA-1. They published in 1993. But the moment they published, they also know there was a possibility for collision on this one. So in 2005, it was shown it's possible to muster the necessary computing power to find a collision for SHA, because as computing gets more powerful, right, it's possible that, those things we think, it's in, before you could reach here. Think what will happen when quantum computing becomes a normal thing, right? In quantum computing, you know how, in terms of crunching data, that's where it excels, right? Because you just have to crunch that data. So by the time it becomes normal, I think that's why we have standard. In Bitcoin, in BSB, we have what we call the Technical Standard Committee, the TSC. So they're in charge of making, bringing in new standards. So you guys in the industry, you guys working, you might say, hey, we need to standardize how this thing is done. Like identity issue, for example, for people want to do identity management program solution in this course, I'll think you look at the more low level part of it, because we first need to develop a standard. Remember in that session we have with the BSV team, right? I think it was Todd, yeah, it gave us some hiccups, some roadblocks in the identity. There are so many things you have to fashion out first, what the standard for this, how do we try, what is even our base case for identity? Is it the national ID? Is it? So these are some of things we need to work out, because it's not just, hey, I have an identity stuff. Well, whatever you have has to be used nationally for it to make sense, right? So we still have to come low level and look at, okay, what proposals can we give so that this can interoperate with, say, the NIN, for example, right? Or do we have to come up with a new standard that will make this thing to work? So these are critical things we have to look at, even if your project just means solving that bit part where we have some standard established. Okay, based on this standard now we can build. So if you can do that standard, maybe subsequent cohort can now do the building. It's still, you still be part of the whole stuff, because you need the standard. In software, one person doesn't finish everything, right? So you do your bit, but you're part of the team. The next guy comes, we say, hey, there's a problem, continue from here. All of you are still part of the team that will go on to do that, right? So standards, very important. So about 2011, it was deprecated, and its use was disallowed for digital signature, because they found out that in 2020 was actually demonstrated that with 100,000 USD equipment, you'll be able to do a collision attack on SHA-1 hash to produce the same SHA hash value, okay? And what does that, remember what we say, collision attack just means you store the value using a particular key, right? Okay, you stored it in a particular bucket. Now, you can make another thing that is different, another value that doesn't hash, but it will hash to the same bucket. Again, that's collision. So it means you can replace the data and it looks like it's genuine, because we know that, hey, once you hash something, collision attack, you cannot have two different things, going to the same place. That's what we assume. But what if it gets so powerful, like it happened in 2020, just recently, you could imagine that 10,000 USD machine can be able to do this, right? And that's how we moved on from that. And then we move on to SHA-2, Secure Hashing Algorithm 2. Now this SHA-2 it's a family of, you have the SHA-256, you have the SHA-512, but that is second generation of it. That's why I call SHA-2. So it's named after, so in this case, for example, SHA-256, it was named after the digest bit length. SHA-256 produces a 256-bit message digest. This means that SHA-256 has 2 raised to the power 56 possible unique output values. That's a lot. 2 raised to the power 56. And 2 raised to the power 56 is like 1.15 times 10 raised to the power 77. That's so huge. That's a very huge space that, yeah, it's a huge space that before we would be able to find something that will lead to collision, I bet you it will take a very long time for that to happen. So that's why SHA-256 is secure. It's used in use. You can use it to do your addresses. You can use it to do your headers, your block headers and all stuff like that. It works very fine, right? So this implies that SHA-256 has so low probability of two different input values sharing the same message digest. Now think of if SHA-256 is this tough to share, to have collision, what will now happen to SHA-512? That is 2 raised to power 512. That's something entirely, right? So one thing with computing and standard is, as you're making one, you're looking ahead. Okay, what if? And that's why in academics, there's always research. In the academia, they you have annual conferences. You know what they do? It's not just to go and, hey, no. What they do is, during the annual conference, new stuff you've been working on in the field, you bring your work and come and present to your peers. Because it's your peers that will be able to appreciate what you have done, because they're also working the same problem in their lab. And they will critique it. So that's why you come and present your paper first. People will ask you questions and you go. It will not be published. Then they now wait. If people have issue with that, they can now write their rejoinder. No, this is wrong, that is wrong. And that's why the scientific community is very strong and robust, because it's peer reviewed. It's a peer reviewed stuff. Okay. So the last point here says it has a very good collision resistance, that it will likely be quite a long time before we have the ability to find a feasible SHA-256 collision attack. So that's it. So you are good to go. So here, there's an activity we have here to do: generate a SHA-256 hash. So in this case, it's in the portal, it's in the fieldwork portal. You must have seen this if you have done this course already. So it says, here we have hard function map. It's just it's a word. It doesn't mean anything. But all they say, generate a SHA-256 hash for this. And we can do that. So can I copy this? Let me see. Because I want to copy and paste so I don't make mistake. Yeah, I can copy it if I exit the. Okay, let me exit the presenting mode. Now I can copy this. All right. So let me copy this. There we go. Control C. So this activity said generate a SHA-256. In the portal, it gives you a link where you just go and put it. I generate it for you, but practice it and see it. But in this case, I'll just run it from my machine, right? So I copy this. It's just a text. We call it a message. The actual word for it is a message. And this message says, hard function map an arbitrary length input, blah, blah, blah. Just a message. So let's do SHA-256 of this. Go back to my terminal. Clear up all these things. Maybe I should just close this Explorer so I have more space. Yes. And see if I zoom in on this more. There we go. Yeah, here we go. Okay. Okay. So remember, we have 2 files already here. Cancel that, please. All right. We have 2 files already, SHA blah blah 1 and SHA underscore something something 2, right? So let's override those 2 files. So again, I use echo. Echo is just a way to send your whatever you give. Echo is a command in the terminal. Whatever you tell it to echo, it will echo. Echo means send this thing to any output. The output could be screen. You send it to your screen. The output could be to a file. It could be to an error. So whatever, you can direct it anyhow. So I say echo, I give it a string, I close it in double quotes. Now I've just pasted what we have. That's it. I close the double quote. So echo whatever this message is. So I want to override. So I'm using single greater sign. If I want to maintain what was there before, I use double greater sign. This means if we go to the next line and write this new one, but I don't want what's there before. I want to overwrite it. So I'm using a single greater than sign here. And we are saying to hash blab, oops. We are saying to, oh, no. I think, okay, SHA, this file started with SHA. Oh, here is it. Yeah, we're sending to the first SHA stuff. Good. Let's confirm that. So cat this first SHA.txt. Yes, hash function map arbitrary blah 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 output. Correct. I clear my screen again. Okay, so the second one, let's do the second one. Let's write the second one rather. Oh, this one is small. I am a short string. I can type that. Let me just type it out. I am a short string. So come back here. I want to echo in quotes. I am a short string and close it. And where are we sending it to? The second star blah blah text. I can call it to. Here is it. Enter. We confirm that cat star something underscore 2.txt. I am a short string. We are good. Let's clear this again. So we want to hash this now. They say we should. The question says use. So let's look at the question together again. It says generate a SHA-256 hash of the following. So let's do for the first one and see. There is it. So I do SHA, no, open SSL, that's the program. Open SSL and SHA-256, and the first text. That first text. Let's see what we have. There is it. So look at the fingerprint, the digest. 34BE, blah, 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 and end with E632. Good. Let's do for the second one. I can just call this my command. Now add 2 here. So I don't have to retype it. Enter that. Okay, let's compare them. The first one start with 34B. This one start with BDD. This one is so they're totally different, not even related in any way. So that's what happened. That's the exercise. So you could try it from your machine, install OpenSSL if it's not on your machine, then use it to run that. In advanced, I think advanced way of doing this could just be to write a Golang program that will do this, but you have to bring in the libraries. There are some libraries that will bring in the binary, the byte string in. It's something you have to look up. If you bring in those libraries and run it, you can write as a program. It won't be manual anymore. You just maybe call it with inputs. Put your, you can have a file that has this thing and we run it for you. So that's the exercise. Come back to the presentation. Okay, I'll go back to presentation mode. Present. Okay, here we are. So we've done with this now. So that's what we call the double SHA-256. So when we do SHA-256, we use the hash function to get the digest of whatever it is. Now you get the digest. Now again, you hash that digest. So that's why we call it double. So you first do it, you get that fixed length fingerprint, you hash that again, that fingerprint, you now run SHA-256 on again. That's why I call double SHA-256. Or #256. Remember, #256 means you have hashed it. Now, go and hash 256, the same thing. All right. So it's a common way. When you see #256, it means double. Okay. So in Bitcoin, the double hash of SHA-256 is commonly written as SHA-256D, but it's not okay, or abstracted to a new function called #256. So how it's easy to remember this. SHA-256 is the base. SHA-256 is the first function. You run it. When you see SHA-256, just run. When you see #256, mean hash that your SHA-256. So you know it's double. So you hash it the first time, you get the digest, you'll go again and hash that digest. That's what the double stands for there. So #256 is used to generate transaction IDs, including Merkle truths. We'll look at Merkle roots in a separate, Merkle tree is a separate program of course. So you can use to generate block header IDs. Block header IDs are used to find a proof of work solution. So whenever you see transaction ID, you should know that it's a #256. It's double, it's not single. It has been hashed and the fingerprint hashed again. And when you see block header IDs, just know that so they are double SHA-256. Yeah. Okay. This is just for informational purposes, so you can understand these things when you do that. So activity generate #256 message digest. So that same things we had before. Now we want to generate their function. Okay. So we'll still use the same file because the same information we have on them. But what we'll now do, first we'll have to make another file. So the output of this, we store it in another file so that we can hash that file and see. Yeah. Okay. So let's go there. So I clear up everything here. Right. So yeah. Open SSL 256. And what file? The first file is the .txt. Yeah, this holds the first text. Now I want to store this output to a new file. What shall we call it? We call it now hash. Since this is SHA, let's call it #256.txt. So I send it to, it doesn't exist, but one good thing with command line is it has to create, we create it automatically for us. So let's call it #256 because we'll have two of them. Okay, 256, the first file .txt. Yeah. Okay, let's see. So I want to cut. Let's see the value in that tower. #256, blah, blah, blah. I don't like this naming. I have so many other things with that. Okay, 256. That's okay. Let's cut this and see. Yeah, what do we have there? Oh, we need to cut things out because you see, we don't need this part. We only need the fingerprint, right? We only need the fingerprint. So, okay, one thing I could do, let's just remove the VI. That'd be two. Let's just go there, pull up the file. The file is there physically, right? So I just pull up the file. We call it hash. Where is hash? Here is. Can't find. No. Hold on. PWD. Let me clear. There this. PWD. Where are we at? Yeah, blockchain scholarship. That's where I'm looking for the file called hash. Oh, here is it. Here is it. So what I said we should do, we could just go directly, and I don't want to use VI and start working on it. Here is it. I did not select it. Okay, here we are. So let's just delete this part, because remember, this is part of the output. So I just want to delete this. So it only has the keys only. That's what we want. So I'll save this file. I've saved it. Yeah. So let's make a second for the second one now. We add that. So for the second one, we want to do open SSL *256. The second file, that one that has short something, we call it 2. Yes. So, but we want to store this in, we call this one now #256.256. We call it 2.txt. So whatever this is, send it to this place. It has done that. So let's go and clear up this other part again, leaving only the yes. So here we are. Control S. I save that. Now I can close the Explorer so we have more space to work, and we expand this one. Not interested in looking at the files anymore. Okay. So what have we done? We have done the first *256 on both files, right? And we have the fingerprint. Now we are going to do the double SHA, or the #256 as it's called. So we also say open SSL *256. And what file are we passing now? We are passing the #25. Let's pass the first one. Yes, .txt to it. Okay, look at the fingerprint. So what we have this time around is the *256 or the double hash, because we first hashed the message, stored it in this text file, right? And then, but it wrote some other metadata to it. We said blah blah blah. We went and cleaned up those. We only left the fingerprint. Now we did that the second time I got it. So let's do it for the other file. Just call back the last command. Change this one to 2, because the other file we named it 2. Oops. Yeah, and we run this. Okay. Anyway, it's a fixed length. Even though it's double, there's nothing there that tells you, hey, this is double. But it's your implementation, you know it's double. So we have these 2 times. And you know what this does? Because it enhances the security. It's not just the first one, okay? It's doing the second one. So it's like doubling the security in it. And you should take note of this. This is another way of, hardening it up. If for some reason there's collision happen on the other, you now did it the second time again, right? It makes that more remote to happen. Okay, clear my screen now. Never mind. So get back to the, yes. So we are done with this. Yeah, we're done with this message digest. Okay, yeah, in this part, I needed to pull off it's a very long table we have, so I want to pull it off from the fifth work portal. My next slide here. So let's go to fifth work. Here is it. Okay, it has a very long table. So I just want to run it from here. So let's look at Bitcoin transactions. Okay, so and *256. So what is a transaction? First, we know that Bitcoin, it has a fixed supply. That's 21 million. 21 million. But then the unit of Bitcoin, just like in Nigeria, the unit of our currency is the Naira, right? You have the Naira and Kobo. The smallest is the Kobo part. The Naira is the higher one. The Kobo is 100 kobolds make 1 naira. But in this case, 1 times 10 raised to power 8, that is power 8. Power 6 is 1 million. So this is 100 million. Yes, because 1 times 10 raised to power 6, that's 1 million. So power 8, you add double 2 zeros, that's 100. So 100 million Satoshi makes 1 Bitcoin. So when you're looking at transactions, they are usually denoted in Satoshi, except, for readability. For most Explorer, they will use it in Bitcoin, so it's more readable. But implementation-wise, right, it looks at them in terms of Satoshis. So 100 million Satoshi is equal to 1 Bitcoin. That's why here we have this trillion or quadrillion, 1, 3, 3, 6, 9. This is billion here. This is trillion here, you see, and that. So, yeah. So 100 million Satoshi makes 1 Bitcoin. So what is a transaction exactly? So transaction, they act as contracts complete with how many Satoshis are being transferred, from where the Satoshis are coming from, and to whom the ownership is being transferred to. Each transaction holds an arbitrary number of inputs on spent transaction output, UTXOs, which include a puzzle. Let me just say this in a simple language. So a transaction is when you want to when you want to transfer ownership to. I like using more of that word ownership because it's not only digital cash we're doing Bitcoin. Remember, we'll be doing identity management here. We're doing product traceability on the blockchain. So for that, you are not actually transferring, using the UTXOs. There are some transactions that they know they are not spendable transactions, right? They are handled differently. We'll get to that in the infrastructure cost, right? So you want to make payments to someone. Okay, you want to transfer ownership. So you say, okay, what are you transferring? So I want to transfer blah 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 is XYZ. That's part of the transaction, right? XYZ to who? Oh, to this person. You put the person address in it. What are the conditions for this to happen? If it hits so amount happens. So you write all those codes, all those things. After doing it, it creates a puzzle. And because you use that person's public key to generate it, okay? So that public key is used to, to sign it, and only the owner of that public key can unlock it. Why? Remember, it's only the private key that can unlock something that's on a public key. The public key is for the public. You can see, we're already seeing it. Your address is double hash, right? You see it, but it doesn't mean anything to you, right? It's just some bunch of numbers. It's only the private key from which that public key was generated, because each public key is generated from a private key. It's only that private key from which it generated that can unlock it. And that's where the whole security about blockchain comes through. Okay, so a transaction, when you bring all the conditions of what you want to do, it can be anything. It must not be transferring Bitcoin to somebody. No, it can be anything. It can be storage. It can be whatever. After doing all those stuff, we puzzle, right? And you send that, and you now send it out on the blockchain. That's what a transaction is. Okay, you do finish the whole thing, got the puzzle, and whoever owns the private key, what you have done, you transfer the ownership to whoever owns that public key, the private key to the public key. So it doesn't physically leave the blockchain and go to someplace and say, no, it's still there in the blockchain. It's just there on the blockchain where it is, only that ownership has been transferred from you to another person, and you don't have access to that anymore. It has gone, it's no more yours. Once that transaction goes through and goes into the blockchain, or the site got spent, it has gone out of you. It doesn't belong to you anymore. It doesn't matter where it's sitting. It's the person with the private key that now owns that thing. So transaction, it mustn't be sending money to somebody, okay? Or it's just those conditions in which you want to execute a contract. That's what a transaction is. And the blockchain keeps track of all unspent transaction output, UTXOs. Whenever something wants to happen, before you broadcast any transaction, they will have to make sure that all the UTXOs haven't been spent. If anyone has been spent, automatically it becomes invalid. Block won't even take it. You don't talk to it. It's just invalid. Nobody will even, no node will be able to take it up for you, right? So the locking script resolves to either true or false. So once it's locked, it's only the owner of the private key that can unlock that. Okay. So if it's true or false, that's the end of the day. So what happens inside it? Do you see why if you make a transaction of, let's say, 50,000 USD on the blockchain, is the same, this fee, the charge is almost the same, not almost, it's the same with making a transaction of just 100 USD. And what matters is the inputs. Why I say almost and almost is the inputs. How many UTXOs are you using? The bytes, the payload. So it doesn't know, it doesn't know, hey, this guy is trying to send 1 million. Yeah, no. All he's seeing is the payload. Oh, it's 19 kilobytes. It's 191 kilobyte. It's 100 kilobyte. This is 512 kilobyte. So that kilobyte is what matters to, I'm sorry. Okay. All right. So it's on the basis, that basis that it doesn't discriminate how much you are sending to someone. All it knows, all the script you are written, what is the size of that script. And when you are designing your wallet, these are the things you want to look out for. These days, there are ways they kind of aggregate stuff, different transactions come together, then send them out in one single stop. Like people that do payroll, you could combine everything, send them out as one. You now put all the conditions inside it. So it allows that's where the programming comes by. You could, all these wild things in your head. I want to do this. You can program all those stuff in your script, in the Bitcoin script, program everything, and it resolves to true or false and get executed. Every part go where they're supposed to go to. Okay. Okay, here we're looking at this. This is an image here. Let me zoom in on this. I wonder why this guy came up here. I didn't call him. This is not Siri. Okay, this is Apple, so I guess it's Siri. Let me close that. Didn't know when I pressed it. All right, I zoom in on this. Let's look at this. Well, you have this image already in the portal. It's the same thing. So here is the owner's public key, the person that owns this. Get other inputs here and hash them together. Sign it with the owner's signature because that's what says yes, it's valid, right? And this is the owner one's private key, does that. So this is the owner two that's going to go. Owner two, whatever input comes out here, we got hashed also, and you have its own signature. So bottom line is your private key that will unlock whatever script has been written. You have to unlock that script for it to be valid. It's either true or if you unlock it, it's true. If you can't unlock it, it's false. Okay. So, and then we have different types of transactions. We have pay to public key hash, right? So in this case, you are paying to the public key, which is your address. Okay. And you also have the one you pay to. Okay, let's look at one transaction here. Now, this transaction here, okay, pay to public key hash. So P to PK means you are paying to somebody's address. We'll have another variation where you pay to script. Let me see if it's down here. I think it's another slide. 1 minute, I'm just scrolling down. No, it's another slide. Yeah, it's another slide. Okay, let me just come back here. We'll just explain some of these things here. And call it a day. So for PKP, you are paying to public key. I told you also you can pay to a script. When you're paying to a script, you are not paying to a particular someone. So you could write your script that will execute. And that script execute and run whenever program is inside it. So it mustn't be to a particular somebody's private public key. You can also pay to a script. And that script, you already written everything. That's the contract. That's the Bitcoin script we're talking about. That's where you do your logic. You put all the logic you want inside that script, right? So when it executes, it will run that script and your stuff will go. It could be, your script will be about election stuff. It has data about the whatever. Hey, again, I'm coming back to that ID. So I'm making this comment in relation with the project we are going to do. So even people looking at, you want to do election, okay, you want to build blockchain solution for voting blockchain. So what's your primary ID? That's where the whole ID comes in again. So identity management, please, you guys should look into it. Identity management is a key part of, I think if we have some group that want to do things about identity management, even in low level, I think the BSV people that will mentor this project, I think they will be able to support us on that. But what I noticed that identity will manage a lot, will solve a lot of problems for us. If we solve identity, come up with a framework and standard for it. So voting could be based on that identity. You see, it plugs in. So yes, you could actually do your voting stuff, right? And leave the room for what are the standards surrounding the identity issue, because somebody's gonna vote. How do you handle the identity of that? And that's what I want us to, that's what personally I'll be talking with the BSV guys. What kind of standards do we have to come up with? Because if we can solve identity, so many things will run upon identity. So many things will run on it. So it's a very big stuff, solving identity issue. What I mean that the standardizing it, having the baseline for that, where any other person building identity-based solution don't have to do everything you have done before. You have done that one, they can just use that, your standard, as API and connect to their own and do. So it will be a kind of a baseline for so many other applications that will happen. Both, I see things about anti-corruption, all of them. They can also run out of your ID standardization. So people working on that. I love that idea. So I think it will come true. Yeah. So in what we are looking here is a hexadecimal representation of a transaction. Hexadecimal, 0 to 16. Yeah, 0, 1, 2, up to. So the last number is F. Yeah, F. So you have A, B, C, D, E, F. It stopped. Remember our base 58 had up to 57. It took care of the core capital letter, but in this case, these are small letters anyway. For hexadecimal, it can be capped small of, it doesn't matter, but it has capital A, B, C, D, E, F. Yes, that is 16. Instead of base 10, it has 16. So the whole of this thing you're looking is written is in hexadecimal. It looks serialized. You know what it is? Look at it here in JSON format. Now, JSON is JavaScript object notation, JavaScript object notation. So it's more readable. This guy, the hexadecimal format is good for machine. Machine will read this quite easily more than this one. But this JSON format is more closer to us. So in the JSON format, we have the version 1. Meanwhile, in the hexadecimal, this 01 here, I mean version 1, plus some zeros added to it, right? So just some differences. So let's look at how many fields we have here. We have version, that's one. Let me say JSON format is just what we call key pair, So key value pair, rather, it's called key value pair. So here is a key, version is a key, and the value is 1. So it's a very common way of API consuming data, just key value, key. Write your API, the key, you can pull up the value from it. So we have version 1, the size 191, the log time. So I'm looking at, we have version as 1, size, log time. Now this V input, this V in is an array. Here is a square bracket. Remember, square bracket is an array. And the array continues to look at where it ended. Look at the square bracket here. So everything here is just one key value pair. Only that inside it, you have other stuff. So you have sub. So we have 1, 2, 3, V in is 4 up to here. After that, we have the V out. It's also an array. V out started here and keep going. Look at where it ended. Look at the last. No. Let me be sure. Yeah, this is the last one because this square bracket here is for this address start here. And so the whole of this V out is once it continues up to this point, then we'll have time, and that's it. So transaction consists of 6 serialized elements. 6 elements. Let's count it. Version is 1, size is 2, log time is 3, V in is 4, then V out is 5, then time is 6. Those are the 6 elements. So that's what we have. So the version is a 4 bytes in hexadecimal 01 because it's version 1. In the JSON format, it's called version 1. It is readable. Here, you already know this is version 1. And why version? Now, version is important. Now, when standard, just imagine that a lot of things will happen in the tech space, in the blockchain space, right? So things won't remain static like this. So at some point, there might be new standard that comes up, right? New ways of doing things. So based on this standard, they might release a new version. And that new version will now have, a standardization, whatever they say, let it be A, B, it follows like that. So for now, we have version 1 and version 2 working with. So in the future, we might have version 5. And in that version 5, what will happen is that we give you more substrates to build your stuff on. You have more standards to build your things on, right? Okay, so that's what the version there is. You have an input count. The V in is only one transaction. We have there. Specify how many input transactions are on it. Let's go back and see. In the V in here, the transaction is just one. Look at transaction ID here. It's just one there. It's just one transaction we have. That's why here it's 1, 0, 1. So this 0, 1 here, after in the hex form of it, from this 0, 1 up to here is just a version. Then this 0, 1 is the transaction, number of transactions. After that, you have a format to read it up, but JSON format is self-explanatory. You can read it and understand it. Okay. You now have the input TXOs, and that's it. In the input TXO, that's why our transaction ID and all this whatnot there. And then we have the output also. Here I have only one output too. And here in the JSON format, it gave all the value of the output, right? Discrete public key, OP, yeah. And all that. Then end log time. The log time, it depends. It's either about the block height or the time. So when it's less than 500 million is the block height. Whenever end log time is greater than 500 million and above, you have to convert it to time, and time is seconds, starting from 1st January 1970. That's how, whenever you see the time, if it's less than 500 million, you know that that time is talking about the block height. Remember what block height is as you're joining the blocks that are growing, right? And but whenever it's greater than that, you convert it to seconds. And starting from 1st January 1970 till date, you now do the conversion and see what it is. So the input UTXOs. Well, you could just go through this. It's self-explanatory, just explaining what's in there for you to understand them the more. So guys, I think we're gonna end here. We also end hash function here also. I expect you can read up the other things. I mean, self-explanatory. I just came in, took this once and explained. So next class will be on Merkle tree. We need to run fast. On Merkle trees, that's also a primitive. So let's understand all those primitives. After that, before we I'll now start the Bitcoin, the infrastructure cost. So I'll just take a look, see if there are a few questions, and we'll try to take them. Yes, one announcement. BSV, they want to organize things for the ladies, for the female, for all the ladies in this course. So I'll be getting back with them on that. I see what date is feasible for them. I don't know what it looks like, but I'm sure it's very interesting for the ladies, right? Maybe they have special opportunity for them. Yeah, I'm not sure, but yes, probably they should. Since they're making it for them, in everything they try to encourage gender, gender participation, right? So, just so we have more of the female people getting committed to the course and getting more excited in it, and hopefully someday I'll have some of our female working in BSV. Let me tell all of you this thing. You see, one good thing about this course, it's not just that you're learning this case. In fact, I keep telling people the end point of this our project. I've got someone complain, oh, this. I say, hey, come on, just go through your course. Go through the course, join the project. That's where the cocoa is, in the project. Because it's in the project that you stamp your mark. Not that what I mean is the project that you will make meaning out, you reap the benefits of this program. Now imagine you are involved in people that will do the identity stuff. And since this is a federal government project and they decide to adopt the standard stuff you guys built, do you know what that means? Just think about it, right? Yes, because identity will solve a lot of problems and you guys are part of people that laid out. Just, it's enough CV. It's like, hey, maybe later on you go say, yeah, we did in your CV, work part of the team that did the framework for identity. That's enough. That's enough sell for you, right? And as more countries are trying to do theirs, you see how you become very sellable. So please, don't lose hope. Don't lose your enthusiasm. The major thing here, I keep saying, is not just that you get your certificate. It's good. But the major thing is that you are part of the people building stuff, the project. That's the main thing. If you just come to your CV, you don't need to suggest that I was involved in project, blah, blah, I did this. That's all. And it's verifiable. Come on. You don't need any other thing. Someone like me, another country, maybe, I don't know, Equatorial Guinea, for example. Oh, look at what Nigerians did. We want to do our own. Oh, they've done it in Nigeria, right? And, oh, you are part of people that did it. Come on. There's nothing more than that. Okay? So please, that's the cocoa in this course, right? So that project part, make sure you participate, be active in your regions, be active in your states. We make sure we decentralize. If you watch, we allow you guys to take lead. We are doing blockchain decentralization. I don't ever come and tell your mentors, hey, A, B, do A. No. Yeah, whatever idea they bring, okay, that looks good. Yes, let's see how it turns out. It's your thing. Own it, right? Own it. Okay, let me just see if I have some questions here. Somebody say, I can't see hash function in my Fitwork. If you cannot see it, just go and go to Fitwork, click on, let me look at that place you're supposed to click on. I'm talking to Dodoski Potoski. Nice. Dodoski Potoski. Just go to Fitwork, search for NITDA hash function. Let me show you. This is Fitwork. It's coming up. Okay. So you can see this here. The NITDA hash function. Look at it, okay? So look for this NITDA hash function. Just register for it. Even if it's not, I know most people it was loaded to your profile, but just in case any course wasn't preloaded to your profile, please just go click on that and register for it, please. Okay. And make sure you're carrying along with your state. Whatever your state is doing, please be involved in it, especially in terms of communication virtually. They say some people are doing I keep seeing stuff. Sometimes I see stuff flash from River State, they have different, I see something healthcare. So I love the idea what's going on there. So whatever your state is doing, please join them. What we'll do at the end of the day is when your mentors will give us your mentors will finally say, River State will say, you are doing A, B, C, D, E, F. We'll say, that's fine, let's give it to us. We'll now collate all of them, right, under broad stuff, okay? And discuss with the BSV guys from there, because eventually they are the ones to mentor it. So they'll have to have some, okay, the A, B, C, D, we go. Then we publish them, right? Then you work in your various groups. Particular guy will work the way you're already working already. The guy in Gombe State, whatever state you are, okay? So just register, go through this course, understand it so that when they are doing those courses, remember, these are primitives. Hash function, Merkle trees, digital signature, that's primitives. You need to understand, you need to know them. Even if you don't understand the technical, just know that, okay, hash function, this is what it does. You have various forms of it. It can be collision, blah, blah, blah. This is why it's secure. We have the double hash of it. Those are the basic stuff. Understand all those things. Understand what digital signature are. Merkle tree, I'll spend time on that. That's a pure computer. It's a data structure. It's pure computer science, data structure. But I'll try to explain it in a layman's way so that you don't need to be a computer science. Just understand, okay, it's a good way of storing data so that it can be accessed very fast and efficiently. That's the main thing. We'll now describe what the Merkle tree is. So if there's any course that's not on your profile, just come here, click that course, register for it, and do that course, please. Thank you. Let me see again. Oh, where 1 minute, please. I'm not sure. Oh, here is it. Okay, so we are looking for. Muhammad Ibrahim said, regards meetup, the mentor have sent letter to facilitate release of her by Jalingo, Taraba State. Okay. Sir, what's your name again? Muhammad Ibrahim from Taraba State. Okay, if you guys still need that, that's fine. Let me just take note of this stuff from Taraba State. 1 minute. Because the next moment I will lose track of everything. And yeah. Please, Mohammed, can you have your mentor send me an email? I think mentors have my email address, please. Have your mentor send me an email, please, so that I'll route that through Harrison, okay? So Shamia Mohammed, but why you haven't have physical one yet, you can be having virtual one, Shamia, please. Virtual one is effective also. So you guys who have time in the whatever time is good for you, it could be in the evening, it could be at night, doesn't matter. Okay, you are in the group or you open up the group and you guys have the meeting, right? If you need Zoom, your mentor can talk to us. We could, set up meeting for you guys, Zoom meeting for you people you can use. So if you get back with or you need to have meeting, but no, even without Zoom, you have if Zoom is gonna be good for you, can give you the Zoom, so you can create a meeting for you, or you can use Google what do you call it again? Google Meet, right? But if Zoom is going to be fine, fine. If not, in your group, have a time. This is project time, whatever it is. All of you come there, discuss. It's a community stuff. Now, let me tell you guys, Bitcoin SV is a non-profit organization. It's not a profit organization. Know this, it's an NGO. Bitcoin SV is an NGO. It's not a profit organization. No, it's an NGO. That's what it is. And that's how it's set up, right? So most things going on here are community effort. Okay? Like I was saying, I look forward to a time where I'll have some of our students working in BSV. Yes, why not? I mean, if you guys are doing everything you are doing now, talking about this wonderful project, and you come up with all these projects you are doing, I don't see what reason why some of you will not work for BSV. I mean, if you're able to solve this identity standardization thing for Nigeria, come on, that's enough. That's enough arsenal in your profile to work in BSV, right? And yeah, also help in other ways to other people. So please know that this is BSV is an NGO. It's not a profit organization. Most of it happens here are community-based, community effort. All right. So take that spirit in your own communities and do stuff for yourself. Whatever you guys doing, you are the one to repeat. Yes, we will repeat because I'll be happy to say, yes, I mentor so stuff. I'll be happy to say that. Yeah, NITDA will be so happy to say, yes, we produce this, right? But at the end of the day, it's you guys. I mean, I'm not going to get anything special for, okay, you know, NITDA's not going to, I don't know though, but what I'm trying to say is that the end user, the end beneficiary of whatever is going on here is you. And you have an open check. We started this course. We said it shouldn't be about certificates. I mean, if it were about certificates, we should have ended, everybody have gone home. But because we want to do projects, we have time to, you know, we have to match our time with the BSV guys. That's what's going on. So if you just certificate, you run the course, we end it, you get certificate, we are done, everybody go home. But what's the point to me is that's not why I put all the time I put in here. So we want to bring in BSV to make sure we do these projects. And they have their own constraints. We can't run beyond their constraints. And that's why, to make sure everything goes fine, we're so, okay, we'll graduate students by working towards, we'll announce the date very soon for graduation. We'll graduate you guys so we know, oh, you are done coursework, certificate, bam. But the major thing is the project, which will now take a life of its own. Okay, because if I don't run it, but believe me, we have finished it. Maybe we're talking about second cohort now, but to what end? Oh, I have a certificate. No, I want you guys to do this project, and I want this project to go into the BSV ecosystem. I want this project to solve problems, to solve Nigerian problem, okay? And that's the case. So please organize yourself very well. You're doing whatever you're putting, you're doing yourself good. If some people are not so serious in your group, it's fine. You be the serious guy. You motivate them, okay? Yeah, and pull them along. You can't do this by yourself. You might have to be in group. So please take your state group very seriously. If you're not having meetup, have a virtual meetup. It's as good as physical meetup. Okay, start with something. Don't wait. Oh, we haven't had physical, therefore no. Have a virtual one and start from there, okay? So let me look at what I have on Zoom. Any questions on Zoom? Okay, I don't think there's questions here. All right, guys, thank you very much. I know it's holiday period is coming in, but we'll still have classes this week again. I'll find out what date it is. We'll announce it just so we could, you know, run through this stuff. Thank you and see you again. Please always check the general Telegram group. That's where we'll send out notification about anything going on. And also your state group, because whatever we put there, your mentor put in your own group. And please, if your group they're not doing fine, you can take charge, talk to your other peers, you guys will arrange things, organize yourself and get going. So see you guys in the next section. Stop sharing and